I will begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I just pray you'd help us today, help us to understand what we're doing, and just to glorify you what we do, Lord. In your name I pray. Amen. Excuse me. All right, so I am going to start by talking about finitely abeliated linear group. Wait, no. Finitely generated abelian groups, perhaps. I'm not sure what I was saying. So what is a finitely generated abelian group? Actually, presented. And so here's the way that. So I'll post this PDF for you guys. I've got this little PDF on how to calculate this, and I'm not. I wish I could tell you the author on this thing, but it's not printed on here, annoyingly. And I think if we Google search it, we'll figure out who wrote this. But I have forgotten at this point. It's really nicely done. I wish I could give credit to where credit's due. But anyway.
Finitely presented just means like definable.
What that means is we can write the group in the following sense. It's generated by x1, x2, xn. Here's your generators. And these are subject to relations ai1, x1, plus. And so we're going to use additive notation because we're talking about abelian groups, right? So these are the generators. These, of course, are the relations, right? And, I mean, how many relations do you got? Well, let's say m of them. So you can arrange these, of course, into the so-called relations matrix, right? So G is essentially described by M by N relations matrix. This is not a kind of matrix multiplication. I mean, maybe I shouldn't even write this, really. Because that's, I mean, we're talking about, what are the difference? These are not objects of the same type. This is not matrix multiplication over a ring or even over a field. I mean, I'm telling you, these are generators. So in some sense, you could think of those as being more like vectors. These are coefficients from relations, right? So this is not the kind of matrix product that we learn about in linear algebra, at least. What should the coefficients be here for this to make sense? What do these coefficients have to be from? Where is the? Yes, the aij's have to be integers. Because we're talking about an abelian group, right? So what's the generation process? You take sums of well, if you're using multiplicative notation, the generation would be something like product of, x1, to the n1, x2 to the n2, xm to the nm, right? If that was a multiplicative notation. But that's the additive generation.
There's really no way to write this as like an actual matrix.
No. Well, not in the traditional sense, but nevertheless, setting this aside, so I probably should put some big old quotes around this because it's not quite, But it is still nevertheless interesting to look at the matrix and think about what do row operations mean to this matrix, right? That's the question. Like, can we understand what the group is by looking at the matrix? And so we don't actually, for examples, it's nicer to use something, so I'll follow his lead. Example 1, if we had relations matrix 8, 0, 0, 0, 8, 0, 0, 0, 8, and 2, 2, 2, all right, then this would be basically describing the abelian group, which has generators A, B, and C, such that what? You've got 8A equal to 8B equal to 8C equal to 0. And 2A plus 2B plus 2C equal to 0. Another example, you could have, I'll start the other way. Suppose you've got ABC such that, 8A equal to 0, 8B equal to 0, you could write the top three in the same way I'm just writing, right? This and this, same animal, okay? So my question is, if this is the generators and relations, what's the relations matrix for this? We have three generators, three relations. So our relations matrix is 8, 8, 8, yeah, 8i, right?
So those have been angle brackets on the left?
He doesn't have angle brackets, but I think Dummenfoot might. It's not an uncommon notation to use the angle bracket for generation, and then to use the slash for like the start is the generators. What comes after that is the conditions on the generators. So, and and I really should. So to answer your question, Sam, yes. I probably should have done that. Thank you. Okay, great. So what is this abelian group? What is any finite abelian group? We already know, right? What's the fundamental theorem of finitely generated abelian groups be? Say, fundamental theorem of finitely generated abelian groups, otherwise known as glove. It says that G is isomorphic to Z to the R cross product with like Z mod, how we go? P1? I guess I'd usually use n's, but yeah, right. And you said where n1 divides n2 divides, n divides nk, right. And nk is the order of tor G, yeah? In other words, the ideal generated by n sub k is the annihilator of the torsion of this abelian group. And this is the invariant factor form decomposition of the module, Z module, which is an abelian group. The what? There's a V? Oh, sorry. S. What's that? Fundamental theorem of finitely generated abelian groups. It's abelian. This is not a serious acronym. Fine, you got me. It's just more fun if you put a B at the end, because you can go, no B at the end.
It should be a G.
Yeah, fine, you got it. Fine. All right, I'm going to stop. Anyway, it's fairly obvious what example 2 is it not?
Z8 cross Z8 cross
I think we have a winner. This is isomorphic to Z8 cross C8 cross C8, yeah. So in other words, S is equal to 0 in this, and we just have n1 equals to n2 equals to n3 equals to 8. All right. So the Smith normal form calculation generalizes to here, although this example is kind of, so like the way Smith normal form works is you look at it, right? You look for the least common multiple of all the entries, right, with respect to the ring, which in this case is the integers. What's the least common multiple of our, excuse me, I said least common multiple, I mean GCD, right? What's the greatest common divisor of the non-zero entries? It's 8. 7. Joe, you plague me to this day. Anyway, that's already in Smith normal form. It's stupid. Yeah. This, on the other hand, example 1 is not, right? So how would you put 8? How would you put the first one into the? What should this be? If we work on that one, what's the greatest common divisor of? What's the greatest common divisor of all these? 2, right? So that means we want a 2 to start with, or possibly a 0. I can't remember exactly how this works, honestly. I'll figure it out soon. But we can certainly, let's just explore a little bit, and then we'll figure out the rules together. But certainly, we should be allowed to flop, listen to me. Flop, yeah. We should be allowed to flop rows. Flip rows, perhaps, would be a more usual English term for that. Swap, maybe better yet. Those are not equal, right? But these are row equivalent. What is that? That operation on the relations matrix just corresponds to saying, reordering them. So that certainly should be allowed, right? And if you think about the relations over the integers, what else should we be able to do with relations? We should be able to add them, subtract them, multiply by what? 1 or minus 1, right? Can you multiply a relation by 2? No, you cannot do that. That would be changing the relation with respect to the Z module structure, right? Take a stupid example. Here of this, I've got A, B, such that A equals to 0. That's my relation, right? And then I go, this is the same as A, B, 2A equals to 0. Well, no, it's not. Having trouble with that. I got curly brackets in my bones. I mean, this is apparently really just what? Z. Because you take pairs and you make one of them 0. But this, on the other hand, is Z mod 2Z, Z. Or, well, vice versa. I mean, you can reorder them, but those are not the same. So we clearly cannot multiply relations by anything that is not a unit in Z. All right, so then what? What can we do? What will we do next year? Well, we can certainly go to what? 2, 2, 2, 0, 8, 0, 1. So I'm subtracting 4 times the first row from the fourth, so I get 1. Oh man, this is bad, guys. This is bad. 8 minus 8 is 0. And so we got like minus 8, minus 8. What will be next? 7. Well, we can also do column operations, as I'll explain. And so, but it's a little bit mysterious right now why we can do that.
Wait, where happened to
Oh, yeah. Maybe I shouldn't do this today. That's definitely also not allowed. You know, can't forget about your relations. Relations are more important than people. Sounds like a very Eastern thing to say. But anyway, makes no sense. Anyway, so we can basically use that 2 to clear these out. And the fact that there's zeros here doesn't do anything. I will shortly try to justify these things I'm doing, okay? So sorry for this cart before the horse kind of calculation, but you'll forgive me. And then, let's see here. Something feels wrong about what I'm doing.
I like that all your arrows are different.
Oh yeah. So they're evolving into some sort of like, you know.
Because we're doing different operations.
Yeah, those are not significant. Those are not like some kind of secret code notation for different things. No, it's just the random symbol generator, which I am this morning. Let's see here. Then we could use that 8 to clear that out, I think. So just adding this to that gives me 0 and minus 8. And then, of course, then we can get rid of that. So we've got 2, 0, 0, 0, 8, 0, 0, 0, 8. And I'm not sure that that's the so-called canonical form for the relations matrix or anything, but this much is true. All right? If the things I just did, row and column operations, are permitted, right? If they provide some sort of isomorphic group, and I will argue that they do, then we've just shown that example 1 is really, we could rewrite it as the abelian group generated by ABC, such that what? 2A is 0, and 8B equals to 8C equals to 0, from which it's manifestly obvious that this is isomorphic to Z mod 2Z cross, well, why am I doing this stupid? Z2 cross Z8 cross Z8, right? And furthermore, if we do this process in the right way, we're also going to get a stack of the invariant. We're going to get the invariant factors, right? Because we start with the greatest common divisor of everything, try to put it in the top, and then kind of work our way down. If we do it in a systematic fashion, we can get divisibility of the first thing, then the second thing, into the third thing. And so like here, you have 2 divides 8 divides 8. So this says that, in fact, the torsion of this group is 8Z, I think. Anyway, it's generated by 8, right? In Z. 8 times anything in the group is 0. All right, so why are these... the row operations are clear, right? Why those should be allowed for the relations. What's not obvious is what column operations mean and why they should be allowed, right? So he has a really explicit, nice example on what that means. And, all right, so let me try to look at it. So he starts out with like a baby example, which I think is helpful. We'll do that to start with. So the baby example of the column operations idea is the simplest column operation you could do would be what? Swap, yeah, the column swap. So suppose you've got, this is his example 6. So suppose you got relations matrix 3, 3, 6, 8, 4, 0, 0, 12, 12, right? And this is, of course, for the finitely presented abelian group ABC, such that, 3A plus 3B plus 6C equals to 0. 8A plus 4B equal to 0, and 12B plus 12C equals to 0. So what if we do, say, what if we swap? He says the effect of swapping the two generators B and C. Let's swap generators B and C. How's that work? He's like A, B, C, such that, and where does he swap them? Not here, okay? So keep this the same. When we say swap generators, we mean keep these labels the same, but swap them over here. If you swap them both places, it's not really a swap.
Is it not?
No. It's just a relabeling. I mean, it's just a stupid new notation for the same thing.
Is that what we were studying?
Yes and no. Wait a minute. Hey, I did not commit to this being stupid. 3C plus 6B, 8A. So we're swapping B and C. BC swap, okay? So 8B plus 4C equal to 0. And 12C plus 12B equals to 0. So I think, and I'm having trouble working this out of my system, you may have noticed. I've got another curly bracket here. It's just drummed into me. If I write element condition, I'm going to put curly bracket after it. It's like in my blood at this point. I've been doing math too long. But yes, okay, so Langle, generators, condition, relations, wrangle. Okay, got it. Now, except for the last one, this BC swap really did create new equations, right? This, not the same as that. This, not the same as that. Right? I'm just saying, this is actually the same equation. It's 12b plus 12c.
Okay.
Is that. And what's the relations matrix for this thing? Well, 3, 6, 3, 8, 0, 4, 0, 12, 12. As you can see, if you flip those, you get back to the original relations matrix. So the effect of swapping a generator is to swap the corresponding columns in the relations matrix. This should clearly be allowed. This does not change the group we're looking at. You could sort of view it as reordering the factors in the direct product, right? Something like that. You know what I'm saying? Okay. Now, the question then becomes, what if you do more interesting things? How does that work out? All right, so this is example 7, which I will now attempt to work out. So his example 7 here, he has the relations matrix 3, 6, 3, 8, 17, 4, 0, 5, 2. All right, and so that's, and he's going back to x1, x2, x3, because we want to do more writing. Such that, you know. Okay, you know. All right, he says define x1 prime equal to x1 plus 2x2. All right. So he says clearly the group G generated by the set x1 prime, x2 and x3, y. Since what? Since x1 is equal to x1 prime minus 2x2, right? So I can get back. The point is that x1 is in the z-span of these generators, so you get x1, x2, x3, which generate the group. So x1 prime doesn't, I mean, that's definitely a generator, set of generators for the group. Because of course you also have 2 and 3 in the z-span of x1 prime, x2, and x3. I mean, are x2 and x3 in there? Yeah, they're right there. Okay, so this is clearly a set of generators. The question is, what are the relations for this, right? What are the relations for this set of generators? Well, basically, we just have to use this, I think, really, right? So we've got 3 times what? x1 prime minus 2x2, right? Plus 6x2 plus 3x3, yeah? We've got 8 times x1 prime minus 2x2 plus 17x2 plus 4x3. And we finally have the much more boring 5x2 plus 2x3. So you guys tell me, what's the relation matrix for the x1 prime, x2, x3 generated group? You can see it from here, right? So we can rewrite this, if you'll allow me this sort of glib notation. x1 prime, x2, x3. So let's see here, I get what, 3 of them? I got 8 of them. I got 0 x1 primes. How many x2s do I got? 0? Yeah. Oh, thank you. 1, did you say? And 5. And, oh, yeah, just 3, 4, 2. So my question is, how do we relate how are these related? If I call the original one, say relations, and call this one R prime, I could say that to get from R to R prime, what did we do here? What was this? So we take column 2 minus twice the first column, right? Or we could say this goes to column 2 just to be more manifest in what I'm doing. I mean, this goes to that, right? Do you guys agree? Yeah, column 1 and column 3 are not changed, right? Column 1 and column 3 are not altered from R to R prime. It's just column 2 we're messing with. And we have subtracted two copies of column 1 from column 2. Yes, we have. That's right. And what was the corresponding? What did we do to the generators? I'll do the easy part. We sent x2 to x2. Right? We sent x3 to x3. Nothing was changed with those, right? What did we do with x1? We set x1 to x1 prime, which was actually what? It was x1 plus 2x2. So contrast this versus, x1 plus, rather, right? Plus 2x2 goes to x2. x1, rather, right? That's our new first generator. I mean, you could say this is column 2 prime and column generator 1 prime to be less confusing. Yeah. You see the interplay? It's a little bit sneaky, right? Column swaps are easy to understand. Those correspond to just flipping generators, but if we replace one generator with a linear combination of another appropriate linear combination, right? Z-spans, right? Then the effect is related but different to the columns. In a very systematic way too, right? You can see you just flip the index, right? And you change a plus to a minus. Like if I had instead said x2 plus, if I had done x2 minus 3x3 goes to, x3 prime, or let's say x2 prime, then that would have done what? Then we would have had column 3 plus 3 times column 2 goes to column 3 prime. We flip the 3 and the 2, we change the minus to a plus, yeah, like that. But the larger point here is you can make these kind of column operations without changing the group up to isomorphism, right? It just corresponds to choosing a new set of generators for the same group. So we're not changing the isomorphism. We're not changing the group up to isomorphism, right? And if we do this systematically, we can put the relations matrix into a nice form, which, will reveal the invariant factor decomposition of the abelian group. This is the point. So you could take this matrix, this more complicated group, and we could do, our row and column operations on it to figure out what abelian group this actually is in disguise. All right? Can we multiply columns by units? Yes. Maybe today's the day I'll finally recover my linear notes. Stupid. I need to open this thing up and run a wire out from it, like literally just solder in a wire, open it up, and but I feel like there's about a 50% chance I'm going to break my computer if I try to do that. So, yeah. So here's the PDF I've been looking at, guys. Finitely generated. Oh yeah, let me. So we were just looking at this example. And I was hoping he would do the operations on this one so we could see what group it was, but he actually did that on a different one, which is fine. I mean, I guess I can just put that on your test or whatever, then we'll find out. I should actually work it out before I do that. might be horrible, who knows. But so starting with this relations matrix, we do like a column swap, then these column operations, then these row operations, then another column swap. And I mean, like, what's he doing to start with? He looks at all these, and you see that the greatest common divisor of those is 2. Because like 7 times 2, 6 times 2, everything's even. 2 is the greatest common divisor. So you're working to put a 2 in the upper corner. And after these steps, he achieves his goal. At which point, you can forget what's above and below and just look at this. And then what's the greatest common divisor of these? Well, 4, right? So then he's going to make row and column operations as are allowed to put that 4 there and 0 out everything below. And then finally, we get 4. So this, and you know what group this finitely presented corresponds to, is isomorphic to Z2 cross Z4 cross Z4. And if you follow these operations, especially the column operations, you can figure out what the original generators map to. You can track the column operations and figure out, like, what did generator A change to over for this? What did generator B? How is generator A and B and C related to, say, generator A prime, B prime, C prime? I mean, you have to track through all the column operations to understand that. But if you do that, you can explicitly generate the isomorphism, sending generators to generators from this to that, which is far from obvious. So that's one thing you can do. The other really neat thing in here, there's more goodness in this this PDF. One of the really neat things, I'll just show you at the end, is he actually gives a example where such groups come up with the Alexander group of a knot. You can calculate something related to the knots. You can come up with an abelian, these kinds of groups we're looking at are associated with how you knot a knot. And so he describes in here how this particular knot, for example, you can see from this knot these relations. And if you do the stuff we've been doing, you can prove that this is isomorphic to Z cross Z cross Z5. That's the Alexander group of that knot.
Is this named after Alexander the Great or an acquisition of Alexander?
This I do not know.
I hope it's Alexander the Great.
All right, now finally, let me go back and address my transgressions from last class. So I have added many examples for you of this calculation, the Smith normal form calculation. So, I think we did this one last time, right? Did we? Or I started it, but I didn't finish it. So here's the full thing. I take the matrix, I do x minus the matrix, that gets me started. At that point, I swap column rows. What I do here? I think I swapped rows 1 and 3 to get from there, right? Then I do these row operations to 0 out below the 1. And then I do column operations to get rid of these, right? Why are those allowed? Why can I subtract? Why is it allowed to say x minus something times column subtracted from the column over there? Like, what kind of module are we working over here? We're working over an fx module, right? So I can subtract fx multiples of columns from columns. Anyway, so using the allowed column operations, which are more carefully laid out in Dummett and Foote, right? He has, if you look in that part of the 12.2 or whatever it is, he has the explicit algorithm. If I'm missaying something, it is corrected there in terms of what is the allowed column operations. Anyway, here are illustrations of allowed column operations, whether or not I wrote the explicit algorithm. Here it is. So at this point, you're left with this. We find what's the greatest common divisor of that. Well, you've got x, and you've got this. These are clearly not having the same 0, so they're not the same linear prime. So the greatest common divisor of the lower 2 by 2 block has got to be 1 again. So I work towards putting a 1 there. And the way to do that, and so this is from Dr. Smith, who is ironically very good at Smith normal form. Advised adding rows here makes that 0 happen because it just makes things nicer going forward. And so I get that 0. And then I do column 3 minus twice column 2 to put that 9 there. I want that 9 to be over here because I really want to make it into a 1. Now, I'm allowed to divide rows. I can divide columns too. Sorry, let me stop saying what I can or can't do. So then this goes to that, and then I use that 1 to get rid of this, and in so doing, I end up putting a cubic down in the lower corner there. And so for this one, I get 1 x times x minus 3 times x minus 6. That's because the minimal polynomial for the matrix is this, because the matrix is diagonalizable with eigenvalues 0, 3, and 6, which I can see from this. I can see from this the eigenvalues are 0, 3, and 6, and it's diagonalizable. Another example. So I decided to do the simple 2 by 2 examples. So diagonal 2 by 2. So x minus 2, x minus 3, and so what I do, column 1 minus column 2 to put that over there, then I add them to give me a 1 here. First of all, when I look at this, the greatest common divisor of these is 1. So I know I need to put a 1 in my upper left corner. And so I do that by these operations. I get to this. Again, this matrix has minimal polynomial, x minus 2 times x minus 3, and it is diagonalizable. In fact, it is diagonal. So can a diagonal matrix be diagonalized? Yes. Okay, that's the kind of deep thought I bring to you today. So here we have your quintessential Jordan 2 block, eigenvalue 3, and I do my Smith normal form, and I get 1, 0, 0, x minus 3 squared. This shows you that the minimal polynomial for A is that, which, by the way, proves that it's not diagonalizable, because the minimal polynomial must be a product of linear factors not repeated if the matrix is to be diagonalized. That's the theorem. But nevertheless, I have the invariant factors sitting there. And I can tell you that we have eigenvalue 3 repeated. And that the geometric multiplicity is 1, while the algebraic multiplicity is 2. All of this I can see from that. You know this one. You love it. This is the real Jordan form of eigenvalue plus or minus I. And so I'm working over the reals, by the way, in case you hadn't noticed. I never stated it, did I? Maybe I'm working over the rationals. You be the judge. But anyway, so Smith normal form, there you go. So the minimal polynomial of this is x squared plus 1. And if I'm working over the reals or the rationals, that's as far as I can go. That's the minimal polynomial, right? There does not exist a Jordan form, technically. There does exist what I call a real Jordan form, as I defined in linear algebra for you guys, if you're with me. Were you with me? Yeah. Everyone was with me. You did. Well, anyway, that is the real Jordan form for complex I, eigenvalue I. All right, so I wanted some more examples. Here's another one. 2, 2, 3, 3, diagonal, obviously. So before we do calculations, you know what's got to happen. The lowest right-hand thing in the Smith normaling must be x minus 2 times x minus 3, because it's diagonalizable. The minimal polynomial will be a product of linear factors, not repeated. And that's what happens. This feels wrong. Curses. This is not right. I don't think this can be right. Because I should have divisibility.
But you forgot to reduce the x minus 2, x minus 3 block.
Ah. Well, so this one's wrong. Okay, this one has an error. Ah, test problem. Fix my error. Example 5 is an error. We'll agree on that. This one is complex eigenvalue 2 plus or minus 3i repeated. And So I'm pretty sure if you do the Smith normal form, you'll end up with this and then that. So this says the minimal polynomial is that, right? And this means that there are, I think it's this anyway. But again, you might want to check me on that. This one is more boring. If I do Smith normal form for this diagonal matrix, yeah. Because what's the greatest common divisor of x minus 3 and x minus 3? Yeah, you see it. This one I'm a little bit happier about because I actually have all the steps, more or less. So if we have a Jordan 3 block with eigenvalue 8, I do my Smith normal forming, I get this. That makes me doubt my previous example. Uh-oh. Phooey.
Going to the third matrix, what is, so what step are you doing right there?
Row 2 plus x minus 8 times row 1.
Okay, why does row 1 change? Oh, I think I'm looking at columns. Okay.
Yeah.
I was looking at columns.
Yeah,
Oh, no.
I kept saying, why does that go to 0 if he's changing
So
this?
my point is, what I was trying to say is, if this is right, it makes me wonder. Let me just say, there's a possibility that there's an error in 6. So you might want to double check me on example 5 and example 6. I could be wrong. Okay. You notice there's a few. I mean, anytime I skip steps here, you got to be wary. Oh man, stupid scanner. So here, I believe, if we look at these two Jordan 2 blocks with eigenvalue 3, it works out to 1, 1. This is x minus 3 squared, x minus 3 squared. So the minimal polynomial is x minus 3 squared, and there's two blocks of those. And then finally, I have some comments about the rational canonical form. Did any of you study with Curtis? Did you study? You didn't. We didn't use Curtis with you, did we? Curtis linear algebra and linear? No. Okay. So this is from before, but in Curtis, for something like, okay, so everyone agrees that this is the companion matrix of a prime polynomial. Great. One's on the subdiagonal, the coefficients over here. There's no minuses because he put the minuses in the polynomial itself. All right? And that is the matrix of T restricted to the T invariant subspace, the cyclic subspace generated by V. We're assuming, of course, that P of x is the order of V. In other words, it annihilates V. So here's some examples of those. Bam, bam, bam. Now, if you think about it, even if f of x is not prime, if you had that f of t acting on x is 0, all right, and if, in fact, f of x is an order, in other words, it's a generator for the annihilator of the cyclic subspace generated by x. I'm using x here where I should be using v, sorry. You'd still get this matrix for that basis. So it doesn't have to only be that p is prime. P could be something else. But here's the thing Curtis does, which messes me up. He, for the case of a repeated prime, like p of x to the e, he introduces this different basis, which is based on descending powers of the prime, like so. And in so doing, he generates this matrix, which is the companion matrix that we just talked about for e to the prime, with superdiagonal nilpotent matrices of order d. This block diagonal structure. This is not in Dummett and Foote, but it is in Curtis, and this is what seeds confusion to my mind, because I remember this. With this setup, something really sneaky happens. In the case that all of your eigenvalues in the field, the companion matrices, what's the companion matrix for if you have x minus a? The companion matrix is a. So these become A. And the B's, what happens in the case, this is your 1-by-1 matrix, they just become 1.
Why isn't B a Jordan block of 0?
1 in the top. 1 in the top.
But you square it and you got 0 right away.
Oh, you're right. It's nilpotent order 2. Thank you. But the point is,
Wait, what? So
this is nilpotent order 2. You're right. But anyway, the point is, if you're in the case where all your eigenvalues are in the field, that means all the prime polynomials are just linear. And these just swap down to numbers, like your in this case, repeated eigenvalue, lambda, 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 lambda. And the b's become 1. 1, 1, 1, 1, 1. And then you're looking at nothing more than the Jordan block for eigenvalue lambda. In other words, with this choice of notation, choice of basis, the rational canonical form becomes the Jordan form. But not for Dummett and Foote. For Dummett and Foote, this is what Curtis does to represent that. This is what Dummett and Foote does. This is the standard rational canonical form. So if you've got a repeated prime, then the companion block you get is this. And then a rational canonical form, you just basically calculate the Smith normal form, and then you make a block one for each thing in the in the Smith normal form. So like here's a typical rational canonical form like that. That would correspond to the Smith normal form for the matrix being something like 1, x minus 2, and then, well, I have to think about it. All right, let me think more about that, and I'll talk to you more about it next time. So we're out of time. So, and then some. Sorry.